Hey everybody! In this video we're going to work through an example where I give you a curve that's a vector valued function, and we're going to find a whole lot of things involved with this curve. So we're going to find like velocity, acceleration, unit tangent vector, curvature, and so on, all the way. If you look down here, keep going. Okay, we're going to find all this stuff all the way down to torsion, which is the how the curve twists or bends. So let's go and start right at the top here and find the velocity. So given our curve, the velocity is just the first derivative. And so we're just going to take the derivatives of the components I, j, k. And so the derivative of 3 sine t is just going to be 3 cosine t. And that's our I component for velocity. And then for j, the derivative is negative 3 sine t. And then for k, the derivative is just 4, so 4k. And that is our velocity vector. Next is our acceleration vector, which is our second derivative of position, or the first derivative of velocity. So if we just differentiate the velocity vector we just found, we're going to get negative 3 sine t for I, and then negative 3 cosine t j. And then the derivative of k is 4k is just 0. So you can write that or just leave it off because that's just a constant. Next is the speed, which is the magnitude of the velocity. So let's go ahead and calculate this magnitude. 3 cosine t squared plus negative 3 sine t squared plus 4 squared, all inside of our square root. And if you do a little bit of simplifying, this is going to be 9 because of the 3 squareds. And then you have a cosine squared plus a sine squared. And so by your Pythagorean identity, that's just 1. And then you have that 4 in the back, so plus 16. So this just becomes square root of 25, which is 5. And so that's our speed. So it's a constant speed that if your object was traveling on this curve, it would be moving at a constant speed of 5. Next is our unit tangent vector. We use capital T for that. And any unit vector is a vector divided by its own magnitude. And so the unit tangent vector is just v divided by the magnitude of v. So we already found the two things we need. We just go ahead and do the division. So this is just going to be 3/5 cosine t, and that's for I. And then plus negative 3/5 sine tj plus 4/5 k. All right, so that's our unit tangent vector. Next, we want the derivative of this vector because we're going to end up using that very soon in the curvature calculation. So the derivative of this vector we just found, just take the components and differentiate. We're going to get negative 3/5 sine t, that's I, and then negative 3/5 cosine tj. And then the derivative of 4/5 is just 0, so we'll just say plus 0k. Next, we need the magnitude of this vector we just found because we're going to use that for curvature. So square root of negative 3/5 sine t quantity squared plus negative 3/5 cosine t quantity squared, all under the square root here. And so if we simplify, we're going to have a 9/25 from squaring, and then sine squared plus cosine squared, so that's 1. And then we end up with 3/5. Okay, so let's go ahead and find the curvature now, or the bending or turning of our curve. And so that's just 1 over the magnitude of velocity times the magnitude of this derivative of our unit tangent vector. And we found both of these values already. So the magnitude of velocity was 5. So 1 over 5 times the magnitude of this derivative vector of t was 3/5. So times 3/5. So our curvature is just going to be 3/25. And remember, with curvature, the larger value means that your curve is turning more sharply, and a lower curvature value means it's more of a gradual turning or bending. Next is our principal unit normal vector, n. And so n, we found everything we need to find this normal vector. It's just the derivative of t divided by its magnitude. So we've already found those things. So let's just highlight that really quick. We have this vector, which was the derivative of t, and we're just going to divide it by its magnitude to get this normal vector, unit normal vector, n. So we just divide out the 3/5 right here. So we're going to end up with negative sine t for I, and then plus negative cosine t for j. And then there was a 0, so that's just plus 0k. So that is n. Next, we're going to move to the components of acceleration. So there's a tangential and normal components for acceleration. And it tells you about how you're kind of moving in certain directions with your turning, because the tangential component tells you about the direction, or you can actually think of it as a change in speed. And then the normal component tells you about the change in the actual turning or direction of your curve. So for these ones, we have multiple formulas we can use. And what I would say is just pick the formula that works best for things you've already found. And so we have some choices here, but I'm going to go ahead and use this version of the formula because it's going to be the fastest. I can use this other one where I find the dot product, but the magnitude of v, we've already calculated that. And so this is going to be really fast based on what we found. The magnitude of our velocity, if you remember what it was up here, it was 5. And so this is just the derivative of 5, which is 0. Again, we have multiple formulas here, and pick the one that's going to be the least amount of work based on things you've already found. And so if you kind of look at our options here, we've already found the acceleration vector, but we didn't find its magnitude. We found this tangential component. So we could use this one. It won't be that bad. This version of the formula would require cross product, which is okay. We just haven't found it yet. But this version of the formula will be the fastest because we found all of the parts that we can plug in there. So our curvature, if we just look back real quick, that was 3/5, or sorry, 3/25, and then the magnitude of velocity was 5. So just putting those two things together, we just have 3/25 times 5 squared. So that's just going to be 3. And so that's our normal component for our acceleration. And so why those matter, when you look at the acceleration vector, you can write it as a linear combination of the unit tangent vector and the normal unit vector. And so we figured out from our work we just did that the acceleration can break down as 0 times t plus 3 times n. So that's another way to write our acceleration vector. Next, we're going to find what's called the unit binormal vector. And so this vector is actually perpendicular to both our tangent and normal vectors. And so we're going to use this cross product to calculate it. We could use this alternate version of our formula, but because we didn't find the cross product of v and a anywhere in our work yet, we're going to go ahead and use this t cross n version of our formula. So setting up my 3x3 matrix to find this cross product, I have I, j, k in row 1. And then row 2 is t, which our t vector, our unit tangent vector, was 3/5 cosine t. The j component was negative 3/5 sine t. And then our k component was 4/5. Let's make that look like a 4. 4/5. Okay. And then our n vector was negative sine t I, negative cosine tj, and 0k. All right, so jumping right into our cross product, when we're focused on the I component, we're going to take the determinant of the 2 by 2 in this corner over here, which is negative 3/5 sine t times 0. So that's just 0 minus 4/5 times negative cosine t. So minus a minus, that turns into a plus. 4/5 cosine t, and that's for I. And so that's our I component. And then next is j, but the coefficient on j is negative. So minus, and let's jump into j's calculation, this component. And so we have, for j, 3/5 cosine t times 0, so that's going to be 0, minus 4/5 times negative sine t. So minus a minus, that becomes plus 4/5 sine t. And that's for the j component. And then for the k component, let's just go ahead and write it underneath here. Plus, this is going to be, let's get rid of some of this work. All right, that's going to be 3/5 cosine t times negative cosine t. So that's negative 3/5 cosine squared t. And then minus negative 3/5 sine t times negative sine t. So two negatives here is going to turn positive, but from our formula we still have a negative. And so that's going to be minus 3/5 sine squared t. And that's going to be our k component for this binormal vector. Okay, let's make this look just a little bit better. And so for b here, we get 4/5 cosine ti minus 4/5 sine tj. And then, actually, that's a 5. Let me make that more clear. And then over here, notice what we get. If we factor out a negative 3/5, we have a cosine squared plus a sine squared. So that's going to be negative 3/5 times 1. So that's negative 3/5 times k, or in the k direction, excuse me. So this is b. This is our binormal vector, our unit binormal vector. Now from here, we're going to end up using this in the calculation for torsion down here. And if you look at this calculation, there's two versions of it. One involves velocity and acceleration, but the other one involves the derivative of b with respect to s, which is arc length. So what I'm about to do is I'm going to parameterize this vector b in terms of s, arc length, so that I can go ahead and take this derivative when it comes time for that. All right, so let's go ahead and jump into that part. So I have s of t is the integral from 0 to t of the magnitude of v. So I just use the letter p here because I have to end up plugging in t, if you notice right there. So I just picked p so I have a different variable. So our arc length parameter s is the integral from our starting t value, which is 0, into t, and it's the magnitude of v, okay? And we'll just say dp, so just sort of rewriting it a little better looking than we had. So this is the integral from 0 to t of our magnitude of v, which was 5 dp. So if we integrate 5, we're going to get 5p evaluated from 0 to t. So this is just 5t. All right, so what does this mean? This means that s is 5t, or if we rearrange and solve, this means t is s over 5. And so this is just a relationship between our input t and our input s, where t, if you think of it like time, and s is like length. You can say for every 1 unit of time, or t, that's 1/5 of a unit of length s. Or over here, every 1 unit of length s is 5 units of t, or time. And so now what we can do with that is we can rewrite b, our unit binormal vector, in terms of s. So all you really have to do here is go back and look at your vector function for b, which we found over here. And where there's a t, replace it with what it equals with s. And so it equals s over 5. And so this is, if we just kind of squeeze it right in here, it was 4/5 cosine t. So that's 4/5 cosine s over 5. and that's the I component for B. And then next was, I'm looking right over here, was negative 4/5 sine t for J. So that's going to be negative 4/5 sine, which was t, is now s over 5. And that's the J component. And then last over here was the K component. It didn't have a t in it at all, so we can just write minus 3/5 K. So this is still our binormal vector. It's just written differently where our input is s instead of t. And again, why we cared about that, why we even did any of that right now, was because we need to take this derivative of b with respect to s to be able to use this version of our torsion formula. So we can use this other version. It's perfectly fine to use this first version over here, but it's going to just be a little bit more work, and it's perfectly fine if you want to do that. I'm just showing you how to do it this way, just in case. So let's take this derivative now with respect to s. So I'm just differentiating this b unit binormal vector, where s is my variable. So taking the derivative of each component, we're going to get negative 4/5 sine of s over 5. But be careful here. Actually, let me make my s look a little different because it's going to look like a 5 if I keep going. You do need chain rule, so that's what I'm saying be careful about. So derivative of the inside is the derivative of s over 5, which is 1/5. So times 1/5. So let me make that pretty clear. The sine is of s over 5, and then chain rule is the times 1/5. And all of that is the I component. And so we'll do the same thing for J and K. And so this is going to be minus 4/5. Derivative of sine is cosine. So cosine of s over 5. But then the chain rule says I need to multiply by derivative of s over 5, which is 1/5. And that is my J component. And then last, the derivative of 3/5 K, that's just 0 because there's no s over there at all. So 0. So if we make this look just a tiny bit better, negative 4/25 sine of s over 5, and that's our I component. Okay, squeeze that in there. And then minus 4/25 cosine of s over 5, and that is our J component. All right, so we're almost to our torsion. And so we just need negative of the derivative we just found, and we're going to dot it with our normal vector n. So let's put those things together. So dot product, so I'm going to take the negative, let's kind of highlight some things, the negative of this vector, and I'm going to dot it, if I go up, with n, which n, where was n? Way up here. Dot it with n. Okay, so remember dot product? You just take the components of each vector and you multiply them and then add. So I'm going to just say, try to remember this, negative sine t and negative cosine t for those components. All right, so we have negative of this component right over here. So that turns into a positive 4/25. And so we have 4/25 sine of s over 5 times negative sine t. Now I am going to adjust for this because I can't have two different variables like this, s and t. So I'll adjust for that in just a moment. So plus the negative of this component right over here. So that's going to be positive 4/25 cosine s over t, s over 5, excuse me, times the J component from n, which was negative cosine t. And then now I'll go ahead and adjust because I don't want to leave s and also t. Let's go ahead and put things back in terms of t. So everywhere that there was a s over 5, remember that it was, right over here, it was t. So I can go ahead and just call this t, and then I can call this t again, since I've already done the work with the derivatives. So then if I multiply this out, look what we really end up with. This is negative 4/25 sine squared t, and then negative 4/25 cosine squared t. And if we factor out the negative 4/25, we end up with a sine squared plus a cosine squared. So this answer is just negative 4/25. All right, lots of work to get here, but we did it.